So, hello everyone. Good morning, good afternoon, good evening, depending on where you're joining us from. It's good to see that so many people have survived the James Webb deadline and are here to listen to some cool talks and for a bit of a change of pace. This is the second SAZERAC-SIP, modeled after the big SAZERAC conference of this summer. It is dedicated to high Z quasars, or high Z really means the first billion years or so, when plausibly reionization was still a relevant process. And before we start, and while other people may still be joining, I'm going to briefly advertise the next two SAZERAC-SIPs after this one. The first one will be next month. It will be dedicated instead to the 21 centimeter signal at the end of January. The abstract submission is still open for just a few days, so there is still time if you want to join that one. And then the following SIP will be called CIDER, and will be dedicated to the cold ISM during the epoch of reionization. So all fun submillimeter and UV transitions that we can observe in high Z galaxies. That one will be at the end of February, and there's still quite a bit of time for the abstract submission. But for now, this meeting will take place over 2 days. We'll have a range of talks related to quasars at early times. This is currently the schedule as it is planned. It has been changed slightly for tomorrow compared to what you may have seen on the website. We have 4 main sessions dedicated to detecting high Z quasars, forming high Z quasars, the hosts of high Z quasars, and their environments as traced by the proximity zones. The SAZERAC series of talks has always tried to give priority to researchers in their early careers, and I think we managed to do that this time again. This is the spread of contributed talks by career stage. You can see there's half of all the talks that will be by students, and we have actually as many talks by undergraduates as by tenure track people, which I think is very nice. And as I go over a few technical details next, I'm curious to poll the audience and see how this spread of speakers compares to the spread of audience members. So the ones of you which are using Zoom should hopefully be able to see a poll on your screen right about now. So feel free to fill it. Okay, so while that's in progress, a very brief important information. We are in a Zoom room. There are currently about just over 100 of us. This Zoom room may fill. If that happens, please go and watch the YouTube stream instead. So if you leave and you cannot rejoin, that might be why. There is a delay on the YouTube stream, which is currently of about 26 seconds. So be patient if you want to ask your questions through there. If you do want to ask the speakers questions, please use the Slack channel so we can keep track of how many questions have been asked, and we will try to not always give priority to the first questions being asked, but really get a mix of participants in there. So please use the Slack channel. If you're not able to do so, you can also use the YouTube chat. We will be monitoring those questions and move them to the Slack for follow-up discussions. There's also other useful channels in the Slack that you may want to use, such as the job advertisement channel, technical support, etc. We hope that you will have good discussions on our Slack. And please be nice to each other. Many of the speakers have not given too many talks before. And here are the results of our poll. So there's a much larger fraction of senior people in the audience than in the speakers. So please be nice to them and make them feel welcome. If you can usually gives a warmer welcome to the speakers. You don't have to. And at the end of talks, participants will be unmuted so that they may have a round of applause if they wish to. So So without further ado, I will introduce our review speaker, which is Eduardo Bañados from MPIA, who has been involved in, I'd say, the majority of the efforts in finding high-Z quasars, and will give us an overview of the field as best as he can in only 25 minutes.
Hi, everyone. Thank you, Sarah, for the nice introduction. And thank you again, and Xiaowei for organizing this super nice program for this SAZERAC meeting. Super excited to be here. So yeah, so I'm gonna try to give an overview of this field in 25 minutes. As Sarah said, this is challenging. So yeah, so I think it's not possible. I tried, but then I decided that it's not possible to do this in 25 minutes. This is good. It's a very exciting field with lots of development in the last few years. And I'm 100% sure that I missed some of your work. So if that's the case, and I think you should be added to these slides, send me an email. I'll try to, if I miss too many references, I'll try to upload an updated PDF of this talk with complete references. And this is also a very observational overview. So if you have some theory papers that should be included here, let me know. All right, so these are the main topics for this SAZERAC meeting, right? So detecting high-energy quasars, supermassive black hole formation, the host of high-energy quasars, and quasar proximity zones. So I think Xiaowei and Sarah did a really great job choosing the talks, and it was, I'm sure, very challenging to decide which topics to discuss during this meeting. Of course, there are many other topics that had to be left out because of time. Maybe there will be another meeting about this in the future. I had to choose what to talk about for this overview, so I'm going to talk about the items here in black. Detecting high-energy quasars, supermassive black hole formation, the host galaxies, and even though it's not in the main topics, it's still related with the quasar proximity zones. I wanted to mention how we can use quasars to prove the intergalactic medium at the epoch of reionization, given that reionization is in the title of this conference. Okay, so let's put this into context. Sure, you all seen a picture like this, the history of the universe. We have the CMB, Big Bang at the left. Then basically for a while, the universe was mostly neutral hydrogen, until at some point, the first stars, the first galaxies, the first black holes start to form. They start to produce the high energy photons to reionize the universe. So this is when the universe start to go from being neutral to ionized. This is what we call the epoch of reionization. And this all happens within the first billion years of the universe. So this is more or less about redshift 6 or redshift greater than 5.5. So this is where this meeting is focusing on, and in particular, this we're also it's going to be very focused on quasars. So quasars are these supermassive black holes that are actively accreting matter, that are growing, and they live in massive galaxies. So this is what we are meeting for. So right. So then the first session of this SAZERAC meeting is about detecting high-energy quasars, which I prefer to call identifying high-energy quasars, because I think the quasars are detected, but the difficult part is to know if they are quasars or not. So just briefly, I want to just for background how we find these quasars. So here in the right panel, I'm showing a typical quasar spectrum. So there I'm highlighting the Lyman alpha line, and then we also see the continuum and other emission lines. And on top of that, I'm plotting filters. So this is the I, the Z, and the Y band. And in the left panel, I'm showing a color diagram. So Z minus Y and I minus Z. So basically, if you have this spectrum, you have photometry of this quasar in these bands, you can measure a color. And this point here is what you measure. And then if you put this quasar at higher and higher redshift, you can repeat the experiment. and basically you know where an object like this should live in a diagram like this. So in principle, this should be simple, right? So if you take images of the sky and select red objects, you should identify hierarchy quasars. In practice, this is not as easy as it sounds, because there are also contaminants in the sky. So contaminants, things that look similar to hierarchy quasars in color space, but they are much more numerous. And these are basically brown dwarfs or M and LT dwarfs. So I'm not going to go into much detail. I think there will be a few talks talking about quasar selection, but this is the basic. And of course, there are new methods being developed using machine learning techniques and also SED fitting. And I think this is just gives you the basis to have an idea of how are we identifying these hierarchy quasars. So we have candidates, but then eventually you need to take a spectrum to confirm their nature. So this is difficult for several reasons. So bright quasars at redshift greater than 6 are very rare. So you expect less than 1 per cubic gigaparsec at redshift 6. So if that doesn't mean anything to you, especially you expect less than 1 per 100 square degrees. So these are the bright quasars. If you go to fainter quasars, then the number gets a little bit more optimistic. But with HST, it's really hard to find these objects. And I think we'll have a talk about finding quasars with HST. So very interested to hear that. And to find these objects, basically, we need large area and multicolor surveys. And luckily, we are in an era of that these surveys exist. For example, SDSS, PanSTARRS, DES, HSC, WISE. So I think a big part of the community is using all of these surveys to find these very rare but precious quasars in the epoch of reionization. So let me just now give you an idea where we are and where we started. So the first quasar discovered in the first billion years of the universe was in the year 2000 by Xiaowei Fan using SDSS. And you can see here, so what I'm showing, can you see my mouse? Maybe not. Yeah, I don't think you can see my mouse, but so what I'm showing here is in the y-axis is UV magnitude, right on the top and faint at the bottom, and then redshift. And the bottom shows how many quasars we know per year. So this was the first quasar in the first million years of the universe. 10 years later, this looked like this. More surveys came online. People started to look for these objects. We were excited. These massive black holes existed in the 1 gigayear after the Big Bang. So 2010, we knew about 60 of these objects. 2014, we were in the 70s. And in the last 5 years, there have been huge progress, and a big part of maybe in this audience, like most of the discoverers of this quasar are here. So this is how this plot looks in the 2020. So this is updated as of today with all the published quasars. So you can see that basically in the last 5 years, the number has increased by a factor of 5. We have lots of faint quasars as well coming from the HSC survey. So this is, now we have actually a sample that we can start to do population studies. And they are spread all over the sky. They are spread all over the sky. So these are ideal objects for multi-wavelength follow-up. So we can, now that we know where they are, and I forgot to say that this is still increasing. I'm sure that 2021 will bring more quasars, have some private communication that will be exciting discoveries. So this is not finished. But once we know where they are, we can point all our favorite telescopes to them and do characterization. And to study these objects is really key to do this in a multi-wave fashion, right? So these are complex phenomena. And depending what telescope you use, you'll see different things, right? If you look at the X-rays, you're looking at the hot corona, jets. If you look at UV optical, then you're looking at the accretion disk. In the mid-infrared, you're looking at hot dust. And if you go to far infrared, then the host galaxies start to dominate. And if you go to radio, then you start to see synchrotron emission and radio jets. So this is just to give you an example that really these objects are bright, and with almost any telescope you choose, you can study them in detail. So this is the X-ray observation of the current redshift record, redshift 7.5. So I wanted to show this because I won't have time to review the X-ray literature, but if you are interested in that, here I'm citing some papers where you can look at the most recent results. Now, if we take a spectrograph, a near-infrared spectrograph, and point to the same object, it looks more like this. So this is more familiar. We saw already a quasar spectrum, typical power law coming from the accretion disk, and on top of that, we have these very broad emission lines. So these objects, I want to recall that these are bright, right? So we are seeing objects within the first million years of the universe, and this spectrum just took 3 hours on a 6-meter telescope. And the nice thing of quasars is that they don't disappear, right? So they're there for a while, at least in our lifetime. And you can go back and look them and study them in even more detail. So this object has been observed by 9 hours or 33 hours. You can see some of papers with very detailed observations of this particular object. And you can do the same with all the other 300s. So now that we have a sample of more than 300 objects, there have been a few papers doing population studies and trying to see if there's some evolution with redshift, the most distant quasars with lower redshift quasars. And most properties at the moment look very similar. So there's not much evolution in many ways. So this is just one example. Here we're showing the ratio between iron and magnesium 2 in the broadline region. So basically this is metal enrichment very close to the quasar. And as far as we can tell, this is consistent all the way between redshift 2 and redshift 7.5. So this enrichment has to happen very, very quickly. There are other properties that seem to be evolving, or at least different than lower redshift. So this is another example. This is magnesium 2 redshift at the bottom, and then blue shift in kilometers per second between carbon 4 and magnesium 2. As you can see, at the highest redshift end, there seems to be many more, like the strong blue shifts up to 5,000 kilometers per second seems to be more common. So this might be that outflows are more common at this early epoch. Other difference that we're seeing now is in X-rays. So if we look at this plot, again, redshift on the bottom and then X-ray slope in on the y-axis, it seems that the slope is getting steeper at redshift greater than 6. The authors of this paper claim that this is not due to new physics, but basically this is a consequence that the quasars at redshift 6 have higher Eddington ratios than the quasars at lower redshifts. So there are some differences, and there are many more. But let me just now go to the second topic of this conference, of supermassive black hole formation. And this plot is basically redshift versus black hole mass for non-quasars. So the blue points, well, all the points here are actual measurements of non-quasars, and I'm highlighting that the two most distant ones known at the moment. So these are two quasars at redshift 7.5, and these are the ones that set the most difficult challenges for black hole formation theories. And the line that I'm plotting in there is basically how this quasar will grow if they were accreting at the Eddington limit the entire time. And as you can see, if you go back in time, if you are accreting at the Eddington rate the entire time, you need to start from a very massive black hole seed. And we also, I'm sure we'll have lots of talks at a different, there was even a poll I saw a few moments ago that still unclear what are the black hole seeds. But I think there is, in the future, it's very exciting. So I think we will find faint high redshift AGN on galaxies, and especially with the new generation of telescopes. And this might give us the clues and see if we actually see these objects, a higher redshift that, according the distribution will depend on what is the actual black hole seed that form these massive black holes that we see today. And identifying them is not only the only thing that is important, right? So we also want to measure the black hole masses, and these objects that are going to have black hole masses of 10 to the 7, a redshift 10, 9, actually will probably need the ELTs to get the black hole masses of this object. So this is, we're looking into the future here. And I'm going to move to the next topic. So quasar host galaxies, there's also an entire session about this during this meeting. And this is basically the summary of the field of on optical or stellar light, right? So we know these quasars we can measure the black hole masses, so we know they're extremely massive, and we expect them to also live in very massive galaxies. And so far, we have not been able to see the stellar light of any of these redshift greater than 6 quasars, even with HST. So this is the idea. So you take HST or any telescope and look at your favorite quasar, try to model the PSF. So this is basically the point source. So the central mass, the central black hole is very compact. And you try to model this as good as you can. You subtract that, and then you hope to see the extended emission from the host galaxy. And that's what you see in the right-hand panel. And until now, basically, we have known detections. I think Madam Marshall will give a talk about this tomorrow. And I'm hoping that James Webb will actually change and reveal the light of the galaxies of these supermassive black holes. But in the meantime, we have been doing some progress on characterizing the galaxies where these objects live. And this is at the moment basically using sub-millimeter telescopes. As you can see in the SED here, if you go to the far infrared, then the host galaxy does start to dominate the emission. And we have telescopes like NOEMA and ALMA that are very, very powerful to study exactly this regime. So I'm going to go through this very quickly. Basically, ALMA, since ALMA, we have revolutionized our understanding of the host galaxies of these quasars. Before ALMA, we knew something about maybe a handful of objects detected with PDBI or NOEMA, but now with ALMA, we have more than 50 detections of the host galaxies, and this is extremely efficient, or extremely quick. In 8 to 30 minutes, you have a beautiful detection of the C+ line. You can have maps, and even all the way to redshift 7.5. The second key point of ALMA is also giving us spatial resolution. So we are now not seeing just a point source. So this is another example of the 7.5 quasar, where we see a complex structure. It has a size. It has also you can also say the dynamics of this object is nothing like a quasi-stellar source, right? So we are looking at one of the first massive galaxies that form in the universe, and it's not a point source. The third revolution is that now with ALMA, you can see, once you know where they are and you know that there is some gas and dust, you can try to see other emission lines like O3 and 2 CO lines on the same object, and then you can actually start to do physics of some of interstellar medium physics of some of the first massive galaxies in the universe, which I think is really, really impressive. And there are only a handful of such studies until now, and we will have a talk about this by Antonio Pensabene tomorrow. So I think this is that we are doing physics just 700 million years after the Big Bang. I think it's just remarkable. And the last topic I wanted to touch, just to try to give you an overview, is how we can use quasars as proof of the IGM. So since the discovery of redshift 6 quasars, we've been using that information to constrain the intergalactic medium of redshift greater than 6, well, even even a lower redshift, right? So this is basically the Lyman alpha forest. And this is just a cartoon trying to show this. When you have a quasar that's very, very far away, the light travels towards us, and on the way encounters some galaxies, neutral gas, and all of that is imprinted in the quasar spectrum, and that's what we call the Lyman alpha forest, which is just in front of the Lyman alpha line. So this provides great information, but at some point you start to lose this, because this saturates when the universe is a little bit neutral. So when you go all the way to redshift 6, basically you don't have much flux fluid of Lyman alpha. This all disappear. So basically we can use that information to know that reionization has to finish around redshift 6. So this is important, but it's kind of frustrating that we cannot use this same powerful method to try to put constraints even at higher redshifts. But there is hope. So from a long time, there has been predicted that there's another signature that quasars will be very powerful to prove reionization even beyond redshift 6. It's called the IgM damping wing. So this is a signature that is evident when you have a significantly neutral IgM, so more than 10%. And basically, when you have a quasar that's surrounded by a very neutral IgM, it produces a particular signature in the quasar spectrum that the shape depends on the neutral fraction of the intergalactic median around the quasar. So we can use that, like if we can find a quasar, a very high redshift, see if we see this particular shape, and then estimate how neutral is the intergalactic median around this particular source in this particular corner of the universe. And this has been used in the last few years quite a lot. Basically, all the redshift greater than 7 quasars that we know show this signature that was predicted more than 20 years ago, but only now we are observing this. And this plot is I took it from Young 2020, that shows all the IgM constraints in the epoch of reionization from quasars. So there you can see that we know that redshift 6 has to finish, and then the constraints beyond redshift 7 are coming from this IgM damping wing. There's a lot of scatter, but it's only based on 4 objects, right? So we really need to find more objects and try to map this. This also can give us an idea how patchy reionization process is. So I think this is really promising, and especially with the new generation of telescopes, that we will find more objects above redshift 7. We will have a beautiful map of the epoch of reionization based on quasar damping wings. But this is not the only way we can use quasars beyond redshift 6 to map the epoch of reionization. There's also another proof that's called the 21 centimeter forest that is similar in spirit to the Lyman alpha forest, but this time you need a radio source, and then you're looking 21 centimeters in absorption. This has also been predicted for a long time ago. And this is a simulation of a 20 millijansky source at redshift 10, where you can actually do this. This is 10 days of integration on 20 millijansky source. This is really bright. So it's promising, but the problem is that you need a bright source in the background in radio, which is not clear if they exist. Until recently, there were no sources at redshift 6 bright enough to do this experiment. But recently, there are 2 quasars that are bright enough that you can actually do this. And these are a quasar at redshift 5.84 and a blazar at redshift 6.1, which is very exciting. So this should enable to do this kind of study. Problem is that these are still a bit too low redshift, right? So they were at the end of reionization. So, but I think I'm very optimistic that we will find more of these powerful radiolab quasars even beyond and study reionization with a different proof. And I also was very excited when I saw this recent paper. There's another idea how to use quasars to map reionization. This using similar concept, but this time the magnesium 2 forest. It's a bit complicated, but the authors here claim that with 10 very high signal to noise James Webb spectra, we can constrain the metal enrichment of the IgM and the neutral fraction at high accuracy. And I would be very excited to know if there are more ideas coming, because I think quasars, even though they're thought to not be the main sources of reionization, I think they will play a role to understand how this crucial phase of the universe happened. So I think the future is very exciting for quasar science. So if you're just starting with this, definitely not everything is done, and there will be many things to be done in the future, right? So many of us were writing James Webb proposals a few days ago. So, and this is just to show you what James Webb will enable on a quasar. This is a quasar redshift 7.5. So basically, until now, all what we know about the quasars is up to 2.2 microns, and redware of that is new terrain, like new terrain for discovery. So James Webb will give us all the optical lines. We might be able to see the host galaxy finally, because the contrast is much better at further wavelengths. So I think there's going to be I hope James Webb will look at a few quasars, and it will be also it's also a very powerful tool to study the environment around these objects. So I show a plot like this at the beginning, right? So this is where we are in 2020. These are all the quasars in the Epoch of Reionization we know. And just want to finish with an extrapolation to what we expect. We know that quasars will provide important constraints on the Epoch of Reionization, supermassive black hole formations, massive galaxy formation. And I think this is not the end, right? So there will be hopefully soon Euclid, Rubin Observatory, and the Raman Space Telescope, and they will enable discovery of more of these quasars, higher redshift and fainter. And this is what it should look like in a few years from now. So I think there's a lot of science coming up from these quasars in the Epoch of Reionization, and I'm going to finish there. Thanks.
Thank you, Eduardo. If everyone can give a round of applause. All right, we have time.
Sarah, you're muted.
Oh, sorry. We have time for a few questions. Huan Cheng Chen asks, can DLAs act as coronagraphs to help resolve quasar-host galaxies in the UV at redshift 6?
That's a great question. I think the answer is yes, and that has been done at lower redshift. Until the problem is that you need a DLA that's very close to the quasar, right? So basically, you need a approximate DLA. And until recently, we didn't know many of those. I think now we have a sample, and it's something that we should look into that. Because basically, every 100 quasars, you find one proximate DLA. And now that we have 300, we have a sample of 3 to 5 where we should take advantage of that as done at lower redshift.
Another question. Can you say more about the stellar masses of these quasars? How are they derived?
Yeah, so as I said, that's also an excellent question, and I hope the JWST will give us a better answer than I can do now. Right, so the stellar light has been impossible to see directly. So what we are doing now is basically inferring the dynamical masses from C+ observations, and then using a conversion to estimate star formation rates. But the direct stellar masses, I think they are still unconstrained.
And the last question, why is there a gap in magnitude and redshift for the predicted quasars that will be discovered between redshift 7 and 8 and magnitude 23 to 22?
So this is the plot I'm showing right now, right? Can you repeat the question?
Why is there a gap in the magnitude and redshift in this diagram? So between redshift 7 and 8 and minus 22 and minus 23.
Yeah, this is by design, more or less. So to create this plot, I use the our current knowledge of the luminosity function. And for Rubin, for LSST, I only estimated the quasars that we will find above redshift 6.5. So I didn't do this for lower redshift. So, but Rubin will observe also quasars at lower redshift. The magnitude is depending on for all these different 3 surveys. It depends on the depth of the surveys. And for the other 2, for Euclid and Rubin, I did also this experiment only from redshift 7, but that's also where you expect, because Euclid is in the near infrared, so it will be used to find quasars above redshift 7. While Rubin or LSST, the reddest band is the Y band, so you using only Rubin alone, the highest redshift quasar you can find with LSST will be 7.2.
Thank you very much, Eduardo, for this very nice overview. Thank you again.
Thank you for having me.
All right. We will now start with the first and the smallest session, which will be our section on detecting high-Z quasars, which follows most naturally from this. First speaker is Takahiro Morishita, who is a postdoc at the Space Telescope Science Institute. And he will be telling us about SuperBoRG and what it can do for research for quasars. Is Takahiro not around? Oh. I don't see him.
He's there. He's waving his hand. You unmute yourself, Takahiro, or maybe asked.
There we go.
Okay.
All right, now I can speak.
Hi.
Let me share my screen. All right, I hope you can hear me clear and loud and also see my presentation well. All right, if that's the case, let's start. Thanks, Sarah, for the introduction, and also to the organizers for this wonderful conference. I also thank to everybody for tuning in this talk. My name is Takahiro Morishita from STSCI, and today I'm going to talk about SuperBoRG, which is our latest program of HST, collecting a bunch of images. And primary focus is on the exploration of luminous galaxies and quasars at this high redshift. Collaborators are listed here, and these are mostly from previous BoRG collaboration. So I am going to introduce this project as well. So, all right. So let's start with a big picture. So here I'm showing a beautiful image of the universe with some of high redshift quasars known today too, and asking myself, why is high redshift so important? Why do you want to find quasars in this redshift? Well, I don't think I need to repeat this, as we just saw a nice review in the previous talk, but just briefly, this epoch, known as the epoch of reionization, is the critical time that the universe transitioned from completely neutral to almost ionized. And we want to know the source that ionized the universe and when and how they did it. So it is important to see and study the source of light from that epoch. In fact, we start seeing some light from this epoch with water field imaging data, for example. In fact, all the quasars here are from ground-based observatories. And then asking ourselves again, why is luminous source so important? Specifically, why do we want to find new high redshift quasars? I think there are two important things that I can say here. The first is, as you see in the left, we can measure neutral fraction of the universe from individual sources by carefully looking at the spectral shape or damping wings. So finding new quasars at this redshift means that we increase the data point, as we see here. At the same time, because these are from individual measurement, and these are independent from the statistical measurement from galaxies, for example, and these are complementary. Another point is, of course, evolution of supermassive black hole. The discovery of extremely luminous quasars at this high redshift imply that rapid growth and possibly very heavy seed mass in the first place too. These findings have actually challenged and also advanced our theoretical understanding too. So to better understand the evolutionary picture and also the transition of the universe, we need more data points at higher redshift, and in particular of more ubiquitous, less luminous population as well. So we are now trying to go beyond the limit, but can we go that easily? So, but it's challenging, as we just saw. This is because beyond the current limit, the Lyman break go into the near-infrared wavelength range, as I'm showing here. And at that wavelength, we start suffering from the significant background sky level, and also the source itself, the brightness becomes fainter as we go higher redshift. So near-infrared filters are available, of course, from the ground, but we may only be seeing the luminous end of this population. And these sources, of course, become even rarer at higher redshift. So we now may need to switch, or at least consider to switch to space-based at some point. Currently, the Hubble is the only facility that can detect such faint light with the wavelength coverage up to 1.7 micron. But its field of view is so limited and tiny, as I'm showing here on the right side. This is a picture of cosmic structure at redshift 7 taken from simulation. And even with the size of candles like here or here, the pointing could fall into the void region, and we may find nothing from HSC that's possible. So as a summary, to go beyond the current limit, we need exquisite near-infrared sensitivity and also wide field survey, ideally from many random pointings, wide field pointings, so that we can minimize cosmic variance and also sample the universe unbiasedly. And that's why we started this SuperBoRG project. As I mentioned at the beginning, we have had actually the Borg collaboration almost 10 years, but that was originally aimed for luminous galaxies, not for quasars, through the pure parallel HST mode. So we have many random pointings all over the sky. And now, after 10 years since we started, we have collected a huge data set, as I'm showing here. And that means that the data set allows us to explore even rarer populations, which is quasars at this redshift. The data set is now in preparation for public release through MAST. So catalogs and images will be published. And of course, these are from HST and there are HST quality. So these are also good for lossy science and intermediate redshift science as well. And I'd be happy to collaborate or just provide this data if any of you are interested in using them. So now let's go back to the quasar search. Did we find a new quasar? Well, the answer is still pending, but we actually found something interesting from the SuperBoRG collaboration. First of all, to search or to select quasar candidates, we apply color cut on the left here, and also morphological selection by looking at the source morphology. The color cut is actually designed to pick significant Lyman break galaxies and also blue UV slope. So the selection window is shown here. One good thing that I like to mention here is that as we go higher redshift, then the contamination becomes less. So here I'm also showing the brown dwarf populations, which we think as a lossy interlopers. As you see here, if we go higher redshift, then color becomes redder, and then it's become more distinguishable, which means that we have cleaner sample. And the same is shown here on the right panel. I'm showing 2 SEDs of brown dwarf and also redshift 8 SED. As we go higher redshift, then Lyman break shift to longer wavelengths. So that will be easier to separate these populations. So from these selections, we found actually 3 point source candidates. We are confident with the number because we also found about 100 galaxy candidates from the selection with extended morphology. So this number is consistent with luminosity function at this redshift. So the number is pretty robust, I believe. And to make sure that these 3 point sources are not lossy interlopers, we also did SED fitting analysis and also astrometry for one of them, because that one of the object has 2 epoch imaging data, so we can just see the difference in the position of the source to measure astrometry. Among 3 candidates, one of the middle one, this one, is particularly interesting because you can see IRAC channel 2 excess here. The flux excess is significant in channel 2. So let's take a deeper look at this object. So here I'm showing the SED fitting result. And at this best fit redshift, that excess can be attributed to the H beta and also oxygen 3 lines. So that is telling us this is extreme object. By taking the residual of the SED versus flux excess, we measure that equivalent width is around 3000. And that is one of the most extreme objects at this redshift, shown in the left bottom. And given the maximum contribution from H beta is not high, it's around 1500 angstrom. So it's fair to think that the ISM of this object is has some contribution from metal and also very high temperature. Another exciting part is that there is a good correlation between flux excess in channel 2 or channel 1 of high redshift object between this and Lyman alpha flux excess. So we are very excited to see the spectrum of this object. But actually, life is not so easy, and we did not see any significant emission from the spectrum taken at Keck. We spent a couple nights and also got archival data from the past years. And now we have in total almost 10 hours exposure of Keck moss fire, but still no emission lines. So this may imply one of the following. Maybe this object is located in significantly neutral region, or the line is actually there, but since it's very broad, we could not detect. But still, we can get some numbers out of this deep spectra and non-detection with simple assumptions such as case B or dust attenuation from SED fitting and oxygen 3 H beta ratio. We can get the upper limit for Lyman escape fraction with this simple formula. But again, this is for unresolved line. and the case would be different if there's broad line. So this is going to be my last slide, but before I end my talk, I like to mention possible nature of these point sources from their number densities. From number densities, we can tell that the population is not likely typical quasars. This is because the number density of lossy quasars. So I'm showing here quasar luminosity function at redshift 6, not 8, but they are much lower than what we found here. The magnitude range is actually slightly fainter for our case. So maybe there is a chance that the slope is much steeper at this faint end. But with current dataset, it's hard to conclude anything. Of course, with Raman Space Telescope, we can do much better. With its almost 100 times larger field of view, I'm showing the field of view of Raman as well as the total area of SuperBoRG. We spent with HST almost 10 years to collect this area, but with Raman, we can do this with one single shot, which is amazing, and I'm pretty jealous about it. So as a conclusion, while we don't fully understand this new population at this point, and we definitely need follow-up observations, I believe our work initiated a new interesting field, especially for magnitude range, where luminous galaxies and low luminosity quasars co-locate. And hopefully follow-up observation will reveal more details about this population and advance our understanding of early source of the light and the universe itself. So I'll leave you with the summary slide, and I'm happy to take questions. Thank you.
Thank you, Takahiro. If anyone can give you a round of applause. I'll start with a question. So what fraction of galaxies at these redshifts which show an IRAC excess don't have Lyman alpha? Hello? Takahiro, I think you're muted.
Sorry, now can you hear me?
Yeah, now we can hear you.
All right, perfect. So I repeat myself. So I don't know exact number for that, but it's definitely interesting to take a look. And my impression, although, is that excess means that Lyman alpha presence. So it's pretty likely, and that's why we were so excited to see Lyman alpha.
And another question. Could these be compact galaxies at redshift 8 rather than quasars? How confident is the point source classification in BoRG, where the data is typically not dithered since it's pure parallel?
Yeah, that's an excellent point. Like you say, the BoRG is not dithered in image, but we are confident with the image quality with some previous tests, and they are actually the point source are clearly selected out of extended sources. But back to your point that how we separate super compact galaxies and quasars, it's difficult and it's challenging with HST by itself. So to do that, we definitely need spectroscopic follow-up for to be sure that what we are looking at is quasars.
Thank you again, Takahiro. Very exciting results.
Thank you very much.
And if the speakers could please hang around on the Slack after their talks, because we have more questions that we don't have time to all answer at the end of the talks. Second in this session is Liliane Nakazono, which is a PhD student at the University of Sao Paulo. She will be sharing a pre-recorded talk, but she will be around at the end to take questions. during the presentation. Talk, but you will be around at the end to take questions.
Hi everyone, I'm Liliane.
During the
I'm
presentation.
from the University of São Paulo, and I would like to first of all thank the organizers for this opportunity. But yeah,
but you will
I
be
will try
around
to
at
answer
the
this
end to
question
take
here.
questions.
How narrowband surveys can provide a better Quasar selection. And I will try to answer that by showing you some analysis we have made based on S+ data, which is a narrowband photometric survey. In that sense, let me first introduce S+ to you. And I would so S+ stands for some analysis we have made based on S+ data, which is a narrowband.
I am hearing some feedback, so I'll try to fix that.
Southern Photometric Local
I'm
Universe
hearing
survey.
some feedback, so
And
I'll try to
although
fix
there is
that.
this local universe in the name, we are trying to find quasars in these observations. And this is actually one of my main goals for my thesis. And S+ is observing the southern hemisphere. It will cover more than 9,000 square degrees with an 86-centimeter telescope. And this telescope is located in CTIO in Chile. So you can see in this picture, this is our dome. And this is an example of an S+ field. This image is from the region of the Hydra cluster. Field, a zoom in of 15 arc minutes. And this is an example of an S+ field. This image is from the region of the Hydra field, a zoom in of in this map, we show our coverage and other surveys coverage just for comparison. So all these red regions in this map will be covered by S+. So I don't know if you can see here very well, but all these fields or tiles are the tiles that were already observed by S+, at least at the moment of the publication of this. So I don't know if you can see here very well, but all these fields are the
Hi, Sarah. Can you hear me? I can share my screen and present it. It's okay.
That would be great if you could, actually.
Yeah, sure. Let me share my screen. Just a second. Okay, can you see it?
Yes.
Okay, thank you. Just a second. Okay, so hi everyone. I'm Liliane. I'm from University of São Paulo, and I'd like to first of all thank the organizers. Okay, yeah, I will try to answer this question: how narrowband surveys can provide a better Quasar selection. And for that, I'm going to show you some analysis that we have made based on S+ data, and S+ is a narrowband photometric survey. So in that sense, let me first introduce S+ to you. So S+ stands for Southern Photometric Local Universe Survey. And although there's this local universe in the name, we are trying to find quasars in these observations, and this is one of my main goals for my thesis. And S+ is observing the southern hemisphere. It will cover more than 9,000 square degrees with an 86-centimeter telescope. And this telescope is located in CTIO in Chile. So you'll see in this picture here, this is our dome. And this is an example of an S+ field. This image is from the region of the Hydra cluster. So you see the whole field here of 1.4 per 1.4 square degrees. You have a zoom in the right panels where I show you a view of 15 arcminutes, a view of 2 arcminutes, and a view of 12 arcseconds. And this map will show our coverage and other surveys coverage just for comparison. So all these red regions in this map will be covered by S+. And I don't know if you can see very well here, but all this field tiles are the tiles that were already observed by S+, at least at the moment of the publication of this paper. So of course, right now we have more tiles observed than that. And the uniqueness of S+ is its filter system, which consists of narrowbands and broadbands. Here you can see the efficiency for all 12 bands, in which 5 of them are broadbands, similar to slow ones, except for the U band, but GRIZ or SDSS-like. And 7 narrowbands that, as I show here, are centered in some important features like H-alpha. And here I show you the photometric depth and coverage area of S+ and how it compares with other surveys. The shape size here scales with the number of filters. Okay, and for the narrow bands, the photometric depth it's typically 20.5 magnitudes, except for H-alpha that is 21 magnitudes. It's above 21 magnitudes. And for broadbands, it's typically 21.5, except for Z-band, that is 20.6 magnitudes. Here I show you some spectra from Sloan for a quasar at redshift 3.42, a galaxy, a star, and a white dwarf. And on top of the spectra, we show the fluxes observed with S+ in each filter. And on the right panel, I show you the near-infrared fluxes from eyes. So we have 12 points there, which matches very well with the spectra, 14 if we consider the first 2 wise bands. And the question is, how well can we classify quasar candidates with a low resolution spectra? And moreover, do the S+ narrowbands play an important role in this classification? Compared, by the way, with analysis with only 5 broadbands. And what about wise magnitudes, for instance? So these are the questions that I'm trying to answer with this analysis. So the first data release is publicly available through this website with photometric data for about 3 million sources in the Stripe82 region. This is not the data set that I used to for the analysis that I'm going to show next, actually. And the reason is because we actually used an internal data release. And the reason is that this internal data release have an improvement in the calibration, but we used the same area, the same Stripe82 area for this analysis. And this internal data release will be part of the future DR2 that will have observations for about 1,000 square degrees. And this DR2 will be available in March 2021, okay? Yeah, so let me go through the classification flow. So basically, I will explain how was our strategy and some of the results. So first of all, we retrieved spectroscopic confirmed quasars, stars, and galaxies that we got from slow-on data sets within 1 arcsecond radius. We also cross-matched with all WISE catalog within 2 arcseconds. And then these are the totals after we applied some selection criteria to get rid of spurious sources. And I also show on this plot the distribution of R magnitudes and spectroscopic redshift. So for these histograms on the side, I show you the distribution for all the objects in field curves, and just for the objects that have a WISE counterpart that I show you in dashed lines. And for a first look of the data, we have done some color diagrams, and this is a first attempt of doing classification. So we found these 2 diagrams that seems to separate well, at least the stars and quasars, which was the kind of confusion that we were most concerned about, because we could use a star galaxy classification before doing a star quasar separation. So here you can see simulated stars in the rainbow colors, in the quasar template being redshift. And besides these models, we have the observations. So these brown points are the observed quasars that this color scales with the spectroscopic redshift. And the blue contour is the observed stars, and the orange contour are the observed galaxies. Well, so these diagrams seems to work well, at least up to magnitude 19. But here we have some caveats that we need to have detection for all these filters, including WISE. And we are also restricted to observations with signal to noise higher than 3, which was one of the conditions for making this plot. And it seems that we have more confusion for magnitudes above 19. So here comes the motivation for using a machine learning approach in order to increase the number of quasar candidates in the catalog. So for instance, we try to build a model that is robust against missing bands, and also a model that does not have to rely on WISE magnitudes. Because for instance, for DR1, we would lose half of the sources if we are only able to classify sources with WISE counterpart. So, okay, next step would be dividing our sample or spectroscopic sample into training and a testing set. And then we run a cross-validation on the training set. So this process here of cross-validation is for selecting the best model. So in terms of algorithm, feature space, and so on. And the models that we compared in the process are so models using different algorithms like support vector machines and random forest. And for this presentation now, it will only show you results from the random forest because it gave the best performances than SVM. And we also compare some feature spaces in order to check the importance of the 7 narrow bands and the WISE bands. So these I show you in the results. So here in this table, I show you the performance of each model in terms of purity, completeness, and F-score. And F-score here is the harmonic mean of both purity and completeness. So basically, if we want both purity and completeness to be good, it can be translated in terms of having a good F-score. And the macro average F-score, that is the mean of the F-scores. So it gives an overall performance, let's say. So for a better view, I highlight here the best performances for each class. But we have to pay attention to the error bars because they can be statistically the same with another model. But in any case, if we see the macro average F-score, it seems that the model with 12 S+ bands is leading to the best performance compared to the models that uses only the 5 broad bands, which is a good thing. So the narrow bands are helping somehow. In the end, these 2 models have similar performances within the error bars. But let's remember that WISE adds the problem that we lose many objects. So if we have two models with similar performances, we would choose the one that could be applied to more objects, of course. So in this case, we would choose the model with that includes the 12S+ bands. But if we now see the classification metrics for quasars specifically, we would see that there is no much improvements. It actually seems that all models lead to a similar performance, at least in terms of F-score. So yeah, through this analysis, we would choose the model that uses the 12S+ bands. And then we go further, and still in the context of cross-validation, we also check the usefulness of some morphological features. I won't show the results here, but it helps. So we included 4 morphological features as well in the classification. And then we finally get the final performance of our model by applying to our testing set. So this is a blind test process to get a more realistic and less optimistic performance of our model that I show here. So we end up with a model that the expected performance is 93.48 purity and 97.87 completeness for quasars, and an overall performance of above 97%. And we can also estimate the feature importances from the random forest model. So here we see that the age alpha filter is the most important for the classification, which is very interesting. Shows clearly how this narrow band specifically is helping for the classification. And just to mention, we are also working with photo Z determinations, also using machine learning. At this point, we reached a precision of 6%, and it goes down to more or less 2% in between redshift 2 and 3. But I'm sorry I'm not giving much details about this work because this is still our work in progress. We also have other students working with that. And also I wouldn't have enough time to talk with details about this work. But yeah, so I'll leave you with the summary. And I would like to say that our Quasar candidates catalog will be publicly available with our paper that right now is under the first revision. And about future work, we would like to extend the analysis in order to classify quasars at higher redshift, because right now we are limited to the population of quasars in Sloan, and there's not many high redshift quasars there. So the classification model that we built is not ideal for these high redshift quasars. So what I'm doing is some modifications in the model for that specifically to find high redshift quasars. And I have some preliminary results that seems very good, but it's very preliminary, so I did not show here. And of course, we will try to refine still our photo Z determination, looking for a better precision, so that you will have a Quasar candidates catalog with already a photo Z for them. And that's it for my talk. Thank you very much. Yes, I'm open for questions now.
Thank you very much, Liliane. Everyone can give you a round of applause.
Okay. Well.
So I'll start with the first question. So I'll start with the first question. So in theory, up to what redshift can the S+ survey detect quasars?
So I don't have the exact number right now in my head, but it's we could detect quasars at more or less redshift 5, and so because we would detect the Lyman alpha in the last red filter.
Another question. So from the testing you've done, does the completeness and purity vary a lot with redshift across the SDSS range?
Oh, that's a great question. I didn't take a look at it. I'm going to do that. That's a great question. Thanks.
And from the Slack, JT Schindler asks, can you briefly elaborate on the size of your training sets, Quasars, Galaxies, stars, and where you get their identifications from?
Okay. Can I share really quickly again? So, just a second. So about the training sets and testing sets, so I divided this sample here that I have in a stratified way, so I keep the ratios the same. So I use 75% as training and 25% as testing set. Okay. And just I think this figure also helps to see the distribution of my training set and also my testing set per class. And the identification I got from this lower data set. So I used GR16 for stars and galaxies and GR14Q for quasars.
That sounds very sensible. Yeah. Thank you again.
Thank you.
And I will now hand over to Shawi for the second session, which is on the formation of supermassive black holes.
Right. So now we have 4 theory talks, and I will hurt the speaker about 10 minutes into the talk, that you have 2-3 minutes left, and we can go on the questions. So the first theory talk is from Shingo Hirano, supermassive star formation in magnetized atomic cooling gas cloud. Please go ahead.
Okay, thank you. Can you see my slide, my cover slide, and
Yes.
my tone? Okay. Okay, thank you. So let's click this. Well, first of all, I would like to thank the organizers for giving me the opportunity to make this talk. And today I would like to talk about our new simulation result, which studies the magnetic effect on the supermassive star formation, or the seed black hole of the Heiji quasar. And the collaborator is Masahiro Machida and Chandra Basu. So the key message of this talk is very simple. So in summary, the magnetic effect can support the supermassive star formation by enhancing the mass accretion onto the seed black hole, and also the increase the fragmentation rate and matter rate of the matter rate in the star forming gas cloud. And I will suggest so new prospect that the magnetic effect can relax the necessary condition of the SMBH formation channel. Okay, so so thank you for the review talk. I will briefly summarize the motivation of this this talk about the SMBH formation. So the motivation is what's the origin of the Heiji quasar, which observed as redshift about 7 with 10 to 9 solar massive, so very massive monster black hole. And the problem is the first stage of stars, or first stars, which forms about 100 solar mass cannot grow up such an observed object. Because they can only get about 10 to 6 solar mass if they grow up with Eddington accretion rate, or the limit rate of the mass growth. So if we assume that this Eddington accretion rate, the intermediate mass black hole with about 10 to 5 or 10 to 6 solar mass object is necessary to explain the supermassive black hole. So theorists consider the formation channel of such an object, so intermediate mass black hole, which called as the direct collapse black hole scenario. And in such a scenario, about 10 to 5 solar mass supermassive star can form in the primordial star-forming gas cloud, and which can collapse to the black hole directly with a similar mass, so 10 to 5 solar mass. Okay. And in this scenario, the SMBH can form in the atomic cooling gas cloud, which is the nature is a very hot condition, and such a cloud have very massive gas field which can accrete onto the central protostar. And in such a hot condition, because of the gene's mass depend on the cloud temperature, the mass accretion rate on the protostar increase, and also the cloud fragmentation can in addition, the hot cloud can avoid the fragmentation of the cloud and form the single protostar at the center of such a cloud. So this scenario is maybe okay, but the remaining issue is what is the necessary condition to form such an atomic cooling halo. And researchers consider many necessary conditions to form such an atomic cooling halo. But this is open question until now. Ultimately, we should conclude which condition is the main path to form the SMBH, and estimate the formation rate of the SMBH, and compare the observational rate of the high-G quasar. So this is the theoretical challenge in the current context, I think. However, today I think so we assume the atomic cooling halo can form by some necessary condition, and let's consider what occurs the star formation process in the atomic cooling halo. And after that, so there's one unexpected factor in the star formation in the atomic cooling halo. It is the magnetic effect, and this is the main actor in this talk. Because in the early universe, at the first formation era, the magnetic field is too weak to have any dynamic impact via the angular momentum transfer or and so on. So MHD effects are usually neglected in the star formation in the early universe. However, some theoretical studies show small-scale turbulent dynamo effect during the star formation process can amplify such a too weak magnetic field during the star formation process. And if such a tiny field can be amplified to some strong field once, such a strong magnetic field can affect the accretion, the dynamics, and final stellar mass. So this is considered in the first star formation. So future first star formation process, and in the atomic cooling halos, one study considers such the magnetic effect, and this paper consider the magnetic effect during the collapse phase. So this means they consider the magnetic effect just before the protostar formation, and not consider the accretion phase onto the protostar. So in this study, they don't show the influence or the magnetic influence on the star formation. So we perform the numerical simulation and study the magnetic effect during the early accretion phase of the star formation. So phase. Sorry, this is a motivation. So I will show you the simulation result, and so I will briefly show the simulation setting. first, I assume the atomic gas cloud with different intermagnetic field strengths. And we consider that von Neuburg our gravitational unstable gas cloud with gas cloud with very high temperature as atomic gas cloud. And I will consider the gravitational contraction of such a gas cloud by considering the EOS models and some evolution. And we stop such a gas cloud contraction until the number density at 10 to 16 cubic centimeter, and consider such a dense region as the Staffing region, or having the protostar inside it. And we continue the simulation until the total mass of the dense region have the 10 to 6 solar mass, so the enough mass of the SMBH, or 500 to 100 a year after the first dense core formation. So this second condition is a limitation. It's due to the limitation of the computational cost. So firstly, I would like to show the physical model with the intermediate strength is the 10 to minus 12 Gauss. So this is the normal value in the ID mass, and the primary chemistry. So firstly, I show the 300-year evolution after the first dense core formation. So just after the collapse phase and starting point of the accretion phase. So these three panels show the density and beef strength and the Platon beta value. So Platon beta shows the ratio of the thermal effect and the magnetic effect. Okay. So let's go to the movie. So just after the formation of the first dense core, the multiple fragment can form around the first dense core. And around such a dense cores, the magnetic field can quickly amplify due to the small scale dynamic process, because such a dense cloud can amplify magnetic field by the rapid rotation process. So by increasing the number of fragment and the fragment region, the amplified field region also expand or widen to the outside. So let's summarize in this slide. So during the first 10 years, very dense cores formed at the center of the cloud, and around the cloud, the B field strength amplified quickly. And after that, the number of fragments formed in the cloud, and the amplified B field region or strong B field region expand outside very quickly. Okay, in the next, let's consider the magnetic influence by comparing the physical case and non-magnetized case, or the simulation result with zero magnetic case. So this panel shows the time evolution of the density structure, and as you can see, the overall structure look like similar, and left side and right, and this profile shows the time evolution of the number of fragment and the total mass of the fragment by the solid line, and also the mass of the primary fragment by dashed line. So as you can see, the number of fragment is not is almost similar with or without the magnetic effect. So so this may be a bit irregular. But the mass of the fragment shows a different feature between the two simulation results. So I will explain what's called this. So the mechanism is very simple. So by considering the magnetic effect, the magnetic field can transfer the angular momentum of the gas cloud. And firstly, the mass accretion rate in the collapsing gas cloud can be enhanced due to the magnetic effect. And this results in the more massive gas cloud at the center of the halo. And if it returns the too much gravitational unstable gas cloud, gravitational disk, and it results in the increasing of the fragmentation rate, or the increase of the number of fragments. But such angular momentum transfer also increase the major rate of the fragment. So the number of fragments are similar in the zero magnetic field case and also the fiduciary case. However, the mass of the fragment or total mass of the fragment are different by considering the magnetic effect. So the time is nearly over. So we also consider the simulation. We also calculate the simulation with different inside magnetic field cases. But we find that by increasing the magnetic field, the number of fragments are not so different, which can be explained by the same manner in the previous slide. But the mass growth rate can be promoted by increasing the B field. So this is a very straight manner. So sorry, so time is over. So I will summarize this talk. So a DCBH scenario is the promising formation channel of the massive seed black hole for the high quasar. And we firstly consider the magnetic effect on this channel. And we find the angular momentum transfer due to the magnetic effect can increase the mass growth rate onto the protostar greatly. So comprehensively, this magnetic effect supports the supermassive star formation. In other words, the magnetic effect can relax the necessary condition of the DC-based channel. Okay, this is so that's all. So thank you for listening.
All right, thank you. We can all pause. I just unmuted everybody. And thanks for keeping the time.
Shall we? I think you're muted.
You hear me now? All right.
Yes.
So we have probably, let's try to do two questions. The first one is, I might have asked it, but could you explain why the magnetic field is larger outside high density regions? I would naively expect flux conservation to enhance B field at high density.
Okay, so in high density region, yes. So in low or the outside the central region, the small fragment can form, and the rotating motion of the fragment can amplify the magnetic field by rotating the magnetic tube and amplify the field strength by such a small scale dynamic process. So this is it's okay.
Okay, let's do one more question. So Rafa asked, how can you tell that magnetic fields relax the conditions of the supermassive star formation?
Okay. So by considering magnetic effect, the mass accretion rate on the protostar can be enhanced. So this is resulting in the atomic gas cloud with more lower mass, which have the more which are less or lower mass accretion rate in the without considering the magnetic effect can form the supermassive star. So. So yeah, so I think so by considering magnetic effect, necessary condition becomes is relaxed. So I think so. Some color which can once cooled and not so not fully atomic cooling, cooling halo may form as SMBH. I think.
Thank you. There are quite a few more questions Slack, so I suggest you look at them afterwards. Now let's move on to the next talk, and thanks very much.
Thank you.
So next will be Ricardo Beckman from the University of Cambridge, simulating the origins of the first supermassive black holes. Ricardo, please go ahead. And I'll give you a warning in 10 minutes.
Okay. So yes, my name is Ricardo. I'm currently a postdoc at the University of Cambridge, but most of the work I want to present today is work I did in collaboration with Julian Divrier and Adrian Sliss at the University of Oxford while I was there. Sorry. So this is another simulator talk, so it sort of fits nicely into the context of the last talk we heard. And what I want to discuss today is a fairly simple question, really at the heart of high redshift quasars, I guess, and that is, how did the first black holes become so massive? So this is a plot a little old now. You know, we heard earlier that the sample of high redshift quasars and their black holes has grown massively over the last few years, but you can see that if you look at the distribution of black hole masses on the y-axis relative to the redshift and the x-axis, some of the first objects we found are already as massive as the most massive objects we see across the history of the universe. Now, you know, this part of the plot has now been filled in more, but the basic point still stands. They're all in this region. And that leads to the interesting question, which is, how did the first supermassive black holes get so massive in just about 600 megayears, which is about the time you have between the first sort of plausible black hole seed formation scenarios to the time when we start observing the first supermassive black holes. So how do you make a supermassive black hole? This is Black Holes 101, but sort of very simply is you have to start with a seed black hole. That's a whole field of research, is how the first seed black holes formed at very high redshift. And it's not a topic I want to go into today, because I really want to think about how these seed black holes then grow and possibly become supermassive throughout their evolution. And there's two potential growth channels. You can either merge black holes together to make a bigger black hole, or the black holes can accrete some of the gas from their host galaxies and grow through that channel. And my work focuses on this gas accretion channel, so I will be disregarding this black hole merger channel now, so there will be no mergers, and we will instead think about how you can study the accretion of gas and how much gas accretion might contribute at very high redshift to the growth of supermassive black holes. So as I said, this is roughly the sort of parameter space we have to cover. So this is the same plot as before, now just extended to lower black hole masses and higher redshifts, because in the bottom right corner here, we've got marked sort of roughly the region of where we think the seed black holes might form, both in their redshift and mass range. So they go from these POP3 scenarios, which would form the smallest seeds, possibly at the highest redshift, all the way to sort of direct collapse black holes, which already upon seed formation are several orders of magnitude larger. But even the most massive of these seed channels leave a large gap between where we think the seeds could form and where we observe the first supermassive black holes. And from there, after seed formation, they grow, and how efficient this growth can be in this particular environment is still an open question. People have been working on this for many years, but it's still very much not well understood how much black holes actually can grow via gas accretion. Here we've got sort of a few cartoonish lines where you can roughly see some proposed evolutions, with the Eddington ratio sort of being a measure of how efficient black hole growth is. Generally, Eddington ratios can fall very low, less than 1%, 0.01, even lower. So all of these proposed lines here are very efficient gas accretion, and you can see that really for these black hole seeds to make it to the observed masses, they need to be extremely efficient. The Eddington ratios need to be very, very high. But the problem with studying the gas accretion, and especially the problem with, you know, trying to get that much mass into the black hole, is that the gas that has to be accreted by the black hole has to flow over a very large range of length scales before it actually reaches the black hole. Black holes are massive, but they're incredibly compact, which means that the actual scales in which they accrete and interact are very small. And the gas really has to flow, you know, via from the cosmic environment into the host galaxies, through the host galaxies, past these sort of interstellar scales where all the sort of star formation and stellar feedback goes on. It has to get sufficiently close to the black hole to reach the region where the black hole's gravitational potential dominates the local environment. So it can be attracted into that, fall into the bottom of the potential, and then finally reach the last stable orbit and be accreted. And you can see that even for a very massive black hole, this is a very large range of scales. And the smaller the black hole, the smaller these sort of scales at the bottom end here get. Now, this is a huge numerical challenge for simulations, including all these scales in one go. And which is why typically we're going to have to make a choice on how many of these we include in a single simulation and try to study at the same time. A typical, what we call a zoom simulation, which focuses on individual galaxies at high resolution, tends to cover this range of scales. So it's a choice where we tend to follow gas flows all the way from sort of intragalactic scales through the galaxy and inside the galaxy. But the problem is that you notice here that actually in this particular context, in many cases, the actual scales where the black hole dominates, so where we could really make a judgment on whether the gas is gravitationally bound to the black hole or not, tend to be unresolved in these kinds of simulations. So I spent over a few years, a lot of time and effort trying to push the range of scales we can resolve in a single simulations near the black holes far enough that we can actually start resolving some of the gas flows right around the black hole and start understanding how much of the gas in the galaxy would actually be able to reach the black hole in this particular context. So this is an example. At the top, I've got a simulation minus the sort of algorithm I've added, where you can see on galactic scales, we have beautiful detail. This is a simulation with about parsecs worth of resolution, which is very good for this kind of length scales that we need to follow the simulations to understand black hole growth over 600 megayears or so. But if you look sufficiently close to the black hole, we very quickly start losing information, and very close on the sort of parsecs or parsec scales, there's very little information left since we're only looking at a single pixel. Now with my zoom algorithm, this is what we get. On the large scales, the simulations are virtually identical. We retain a lot of the information, but we were able to add a targeted extra refinement around the black hole that's allowed us to retain and recover a lot of this information right near the black hole as we run throughout the simulation. Which has made it possible to try to study the gas flows from the intragalactic scales all the way to the sort of black hole dominated scales in a single simulation. Obviously at increased cost, so it comes at a price of other, and other trade-offs, but it's still, I think, a huge step in the right direction. And I want to show you today why it's so important that we study gas flows, not just on the galactic scales, but actually on scales much closer to the black hole itself as well. So what I wanted to understand was, how does resolving the subparsec black hole environment influence accretion, particularly in the context of trying to grow the first supermassive black holes, which have to sustain these incredibly high accretion rates over time. So before I get all the way to the, to the early universe, I want to show you a little test case first. So this is the simulations I just showed you the images of. Dark blue being the high resolution case, the beautiful bottom row, dark red being the top row of images, which is the lower resolution. And in all three panels, I compared how the black hole grows in these environments over fairly short time scales. So we're looking at only about 5 megayears here. All black holes start out identical, and then you can see they all accrete very efficiently. So over time, the mass of the black holes changes very quickly. But the first thing you will notice is that, first of all, the lower resolution case actually was more efficient at accreting. That makes sense because gas, we were removing gas on larger scales since we don't have any information on small scales. So the black hole actually grows much more efficiently over time. And the higher the resolution, so the higher the number of the simulation here, the lower the total black hole accretion drops. So there's something there to understand that on smaller scales, accretion becomes harder. The other thing to notice that if you compare the black hole accretion rate over time, which is in this middle panel, especially the red line, which is in comparison to, say, the dark blue line here, you will notice that the red line is very choppy. So the accretion rate very quickly jumps up and down. And that's because on the scales we're resolving, every time a gas clump enters the center of the galaxy where the black hole is, it's immediately accreted by the black hole, the accretion rate jumps up, and then as the gas sort of is gone, the accretion rate jumps back down until the next clump enters sort of the center of the galaxy. But you will notice that in the higher resolved simulation, this is not true. We tend to get these more extended, longer spikes followed by long, low periods where the accretion rates drop much lower. And the reason for that is that if we look at the central region around the black hole, what we start building up very quickly here is we start building up a a nuclear disk. So this is not the accretion disk. We're still at scales far above where you'd think classically study an accretion disk, but this is clearly a disk-like structure in the center of the galaxy, in the potential of the black hole, that is feeding this black hole over time and also acting as a buffer to the accretion. And what happens is, over time, we get gas clumps falling into the center. So this is the plot where we got radii on the y-axis. So these markers here are two gas clumps that fall from large radii, so over 10 parsecs, to near where the black hole is. There's a second one coming in a little later. This is a time series. And as these gas clumps fall in, the black hole accretion rate here shown in the black dashed line spikes up, which is what you'd expect to happen is. But the interesting part is the mechanism of why that happens is, because what we've also shown here is this orange line, which is the outer radius of this nuclear disk. And as these gas clumps come in, it's not just that the clumps get accreted, it's that actually as they disturb this nuclear disk, the nuclear disk contracts due to the transfer of angular momentum in this process, and delivers an extended accretion feeding event to the black hole, which then grows for a good period of time until the disk resettles and the accretion rate of the black hole drops off again. So actually during this accretion event, more mass is delivered to the black hole than is in the individual clumps, and it's much more extended than it would have been in the simple case when we were just looking at the actual, when each clump just got individually accreted as it got there. So what we took away from this is that these sub-parsec-sized gas features in the potential of the black hole can change the black hole accretion duty cycles in a way that's very hard to predict from super-parsec-sized gas features. So basically, there's an amount of information that's very hard to recover from larger scales, which for me is a very strong argument that we do in fact need to go to these lengths and look at these incredibly detailed, expensive simulations to study how these black holes grow in this particular context. So what about the first black holes? Well, if we do put one of these high resolution black holes into a cosmological setting and try to understand, how do we get from this bottom right of this plot here, from one of the seed black holes, can we make it all the way to the observed regime? So this is a simulation, as I said, in a full cosmological context, using the super refinement scheme. Won't bore you with the details, but we basically picked a halo at around redshift 20 and seeded a black hole in it and then let the evolution of it run. Does it grow? This is the interesting part. It does not. So, or rather it does very efficiently early on, but it certainly does not reach the observed mass regime. So this is the total mass of the black hole. We started at about a few hundred solar masses, so sort of in the POP 3-star remnant regime, and we let the simulation run for about 200 mega years, so about a third of the total evolution time to where we see the observations. But then we gave up because, as you can see, the evolution very quickly started stalling. And the reason this is very interesting is because this is still a very simple simulation. So this is a simulation without feedback. There's no stellar feedback. There's no feedback from the AGN. So this is a very gas-rich galaxy assembling at high redshift that should have plenty of gas supply. We see very high sustained star formation rates. This is clearly not a lack of gas in the galaxy. And yet, despite this very simple model where we have removed some of what we know is crucial physics in this environment that tends to suppress black hole accretion, we still don't get the runaway sustained growth that we expected in this particular environment if you look at it at these incredibly high resolutions. So if we go back to this plot, how much did we do on this plot? We started down here, redshift about 19, a few hundred solar masses. There was a very early accretion boost, so the black hole actually grew super Eddington very efficiently as we expected it to. There was not much to hinder its growth, but then growth very quickly stalled. And despite the lack of feedback, we had actually found very low Eddington ratios over time, and we got to about this far, and then decided it wasn't worth the computational time to try to continue since there was very little evolution. And in fact, if you look at the black hole accretion rate, you can exactly see that there was a very, very high initial growth rate. As expected, the black hole was born in a high gas galaxy. But then very quickly over time, we get these incredibly low accretion rates. This is the Eddington accretion rate here in gray. So you can see that the ratio between the black line and the gray line drops very low. And black hole growth effectively stops after the first sort of 50 mega years of evolution. Star formation, on the other hand, continues not completely at the same level, but certainly at much higher rates than the black hole growth. So there's clearly an ample gas supply. And when we try to understand why the black hole doesn't grow, we found that there is a very strong correlation, obviously, between the gas supply local to the black hole and the accretion rate, which makes sense. You know, black hole accretion rate is calculated based on the local gas properties. So if you got locally a lot of gas, then the black hole can grow. But we actually found that the correlation only really holds for very small scales. So in our case, we found a strong correlation between gas mass contained within a parsec of the black hole. But if we go as far as just 10 parsecs away, which on intergalactic scales is not a lot, we found basically no correlation between the gas supply and the accretion rate of the black hole. So that showed us that there is a lot of gas on scales very near the black hole, but actually most of it is not bound to the black hole or not on an orbit where it's able to be accreted by the black hole, so therefore cannot act as an effective gas supply for the growth of these black holes. And a look at the images revealed where, to a certain extent, the issue was. So at the top here, we got a series of pictures that show us 4 different snapshots from redshift 6.84 to 16.18. We can see the galaxy with these sort of beautiful spiral arm structures, and the black hole location is marked with this black cross. And you can see the black hole is certainly in the galaxy. It is certainly near the center of the galaxy, but it's not precisely located at the center of the galaxy. So what ends up happening is that the gas supply of the black hole becomes very, very localized. There are times when the black hole depletes its local sort of orbit almost completely. There are other times when it passes through gas-rich features and able to sort of pick up some extra gas, which drives these accretion spikes that we saw earlier. And then over time, the gas supply becomes depleted again, and the black hole is again not able to tap into this existing gas reservoir in the galaxy. So again, we found that sub-parsec size gas features can change the black hole accretion duty cycles in a way that cannot easily be predicted from the super parsec size gas features. So part of this was that again, we were trying to understand whether we can use the information on these larger scales, since this is what's more easily, more cheaply, more commonly available in simulations, to try to study the black hole growth in these simulations over time. And again, we found that in fact there's very little correlation between the information on the larger and the smaller scales, or at least it's not as simply as linking the amount of gas on, say, 10 parsec scales near the black hole, and that does not provide you a reliable accretion rate onto the actual black hole, even in this incredibly simplified scenario where we've neglected the sort of feedback effects. So in conclusion, what we took away from this is that resolving sub-parsec size gas features fundamentally changes the accretion and therefore possible later feedback duty cycles of massive black holes. Increasing the resolution decreases the gas accretion rate onto the black hole in general. So more information actually makes it harder to accrete, which makes the challenge of growing the first supermassive black holes even harder than we'd maybe appreciated before. Even in the absence of feedback, black holes are not able to grow indiscriminately, because if studied at sufficiently high resolution, the dynamics of the black hole, so where exactly it is located in the galaxy, becomes a much more important feature, again, than we maybe appreciated before, because the gas supply of the black hole is so localized, and its effect on the larger galaxy can be so limited in this particular context. And I'll leave you with that. And
right, so much. Great talk. So you can unmute and applause. And quite a few questions. And we had quite a few questions here. Let me just, because we're over time, let me just one.
Shall you have to unmute yourself when people are done clapping every time? Sorry.
All right. I have to unmute again. Sorry, because we're over time. Let me just ask one. So, Nick, how set up initial conditions, because observed black holes are very rare, 5 to sigma fluctuations. Actually, Tom has a related question of these are extremely rare objects, therefore your answer may be correct, but only sort of usually they don't grow, but in a rare case they might.
Yes, so that is one of the big limitations of this work. So a lot of this was done at a time before some of the results that we now have about the host galaxies of the first supermassive black hole. So I'm thinking of the results from the blue tide simulations. So what we did at the time, we simply went with an overmassive region. So we picked the progenitor of the most massive galaxy at redshift 6 that had the correct number density, following the logic that the most massive black holes are probably found in the most massive halo. But it's absolutely correct that the big problem here is that we might be studying in excruciating detail the wrong area, right? And that is a big limitation. It's something I've been thinking about for a while on how to do that better, because part of the problem with this is that because these simulations are expensive, we can obviously not afford to do them terribly often. So trying to solve the problem of knowing which halo to study before we have to run the simulation is one of the big problems. And definitely one of the big challenges of this work.
Right. Thank you. And there are a lot of more interesting questions in the Slack. So
I'll have a look at the Slack and do my best to answer.
Great. All right. So let's now move on to the next talk, which is from Fabio Di Macchia, the growth of early supermassive black holes relative transfer cosmological simulations. So Fabio, please go ahead.
Yes. Yeah. Can you see my screen?
Yep.
And now can you see the presentation in full screen?
Yep, perfect.
Okay, perfect. Okay. Hello everybody, I'm Fabio Di Macchia. I'm a PhD student at Scuola Normale Superiore in Pisa, Italy. And I'm going to present the work that I'm doing for my PhD regarding radiative transfer simulations of redshift black holes. So I'll give a little bit of introduction. We know so far more than 200 quasar redshift higher than 6. And for plenty of these objects, we also had spectroscopic follow-up that allow us to estimate the black hole masses powering these sources, which were estimated at values around 10 to the 8, 10 to the 10 solar masses. And this is a huge amount of mass for objects that are in place when the universe was less than 1 gigayear old. We saw this in plenty of this talk previously, that if we assume that these objects are of stellar mass seeds, it is very unlikely for them to become supermassive black holes at redshift 6 without into limited accretion. Therefore, this challenges standard model for black hole formation and growth, and probably we need to assume either formation of larger seed or super Eddington accretion. And how can we distinguish between these channels and we can constrain them? Well, we need to look at their progenitors, so we need a strategy to find them. We know that the progenitors of the supermassive black holes at redshift 6, given that structure formation proceeds in a hierarchical fashion, these progenitors should be smaller black holes at an even higher redshift that grow and merge into the larger ones that we finally observe. So a possible strategy to find these progenitors is to start from the multi-wavelength observation that we have at redshift 6. Then we can perform numerical simulations of high redshift that can reproduce these quasar at redshift 6, and we can constrain these simulations with observation. And finally, we can use these simulations to make predictions for observational signatures of these progenitors. So for what concerns the observation that we currently have, I will just give a brief review of what ALMA did in the latest years with that probing far-infrared lines like C+ and oxygen 3, and also the dust continuum, we were able to understand better the physical properties of quasar-host galaxies at high redshift, in particular their gas mass, their star formation rate, and the dust mass. A particularly interesting case that will be relevant for the later part of the talk are these observations by the Carlin collaborators in 2017, and recently there were also other work. In particular, they find for following up with ALMA a sample of 20 quasar, they find 4 objects with a sub-millimeter galaxy companion that was detected in the C+ and in the dust continuum, but not in the UV. And maybe this is an indication of emerging system. In this work, we consider numerical simulations of from Barai and collaborators 2018, in which a 10 to the 12 solar mass halo is followed from cosmological condition down to redshift 6. These simulations are performed in gadget with standard prescription for stellar physics, and also an additional prescription for black hole seeding and growth. In particular, I will focus on two runs that are called the AGN-Sphere and AGN-Con, and they differ for the way kinetic feedback from the black holes is implemented. In case of AGN-Sphere, energy is injected onto the surrounding gas from the black holes in a spherical symmetry, while in AGN-Con, it is distributed in a bicon. This different feedbacks has also an effect on the evolution of the two black holes, of the black holes in the two simulations. In particular, if we focus on the most massive black hole in the two runs, we see that the accretion rate in AGN-Con of the most massive black hole is always higher with respect of the one in of the most massive one in AGN-Sphere. And as a consequence, the same is also true for the black hole mass. At the end of the simulation, the black hole in AGN-Con has an order of magnitude, a mass that is an order of magnitude higher with respect to the most massive one in AGN-Sphere. The gas distribution is also slightly different in the two simulations. You can see the column density of the hydrogen. In particular, the gas distribution in the AGN-Con is slightly more diffuse because of the effect of the feedback. And as a result, also the star formation rate density is lower, and this also affects the total star formation rate, because the star formation rate is implemented in a simulation with a density-based criterion, and therefore a lower density also results in a lower star formation rate. So let me now present you the result regarding the radiative transfer calculation that we did for AGN-Con. This is the tool that we need in order to make observational predictions from this simulation. We consider the hydrodynamical run, so the gas distribution from the hydro simulation, and then we derive a dust distribution by assuming a uniform dust-to-matter ratio. We adopt a model for the dust that is either the SMC1 or Milky Way, and we assign to the black holes a bolometric radiation with a bolometric luminosity set according to the accretion rate from the hydrodynamical simulation. We then use the code skirt to make radiative transfer calculation, and then we finally obtain the observational prediction. Here you can see on the left the UV emission and on the right the infrared emission. What is particularly interesting is the fact that we can identify clearly 4 different sources bright in the infrared, that here I'm labeling with letters A, B, C, and D. 3 of these sources, A, B, and C, are galaxies that host inactive black holes. But you can see that only one of them, that is source A, is visible in the UV. In particular, while the source C is the far-infrared brightest one. So these 2 sources host a black hole that has a comparable mass. It is 2×10⁹ solar masses. But the accretion rate of the black hole corresponding to source C is almost twice the one in source A. However, even if this black hole intrinsically should be the brightest one, it is completely dust obscured in the UV. While another source is visible in the UV and also visible in the infrared. Therefore, this system, that is an emerging system, would actually appear as a Quasar plus SMG companion, consistent with the observation that I was talking before by the Callian collaborators. We can be also a little bit more quantitative by considering the spectral energy distribution of the 4 sources. Here I kept the same color legend, so on the right you can see the SCD for source A in red and for source C in green. Source A is actually brighter than the current deepest HST observation that we have, and therefore would be actually detected as a UV, as a quasar, as a UV source, and source C is consistent with the Carli data. So now let me move on to the other run, AGN-Sphere. If we compare, like on the left panel, the SCD of the 2 simulations, we can see that AGN-Sphere is fainter both in the UV and the infrared. And therefore, of course, it is much easier to detect AGN-Con with optical, from its optical UV emission. But we saw in the previous part that also infrared may contain some useful information regarding AGN activity. So can we understand something regarding AGN-Sphere using its infrared emission? In order to understand this, we consider a control simulation without seeding, without black hole seeding, which is called NoIGN, which that is shown here with a blue line. We then consider the flux in the infrared and in the mid-infrared in the two simulations. And we find that in NoIGN, the ratio far infrared to mid-infrared is 100 to 1000, while in AGN sphere, it is only 10. Therefore, AGN sphere, which corresponds to a faint AGN, has a mid-infrared to far-infrared excess that can reveal the presence of a faint or dust-obscured, in another case, AGN. This is particularly important because this means that if we combine a far-infrared observation like with ALMA with future near-infrared, mid-infrared facilities like JWST, we can be able to unveil faint and dust-obscured AGN. So let me now summarize. We perform a radiative transfer calculation of a redshift 6 Quasar galaxies. We predict from the dynamical simulation merging system that are also consistent with ALMA HST observation of Quasar plus SMG companions. And we also suggested a synergy that can allow us to unveil faint and or dust-obscure AGN by following up with JWST origin galaxies already detected with ALMA. Thank you for your attention. I'll leave here the conclusion. I will be happy to answer your questions.
Thank you very much. Now we can allow people to unmute themselves. And we can all thank Fabio. All right. Thank you. And we have a couple of questions here. First one is, what is the variation of the calculated luminosities depending on the viewing angle, etc.?
Oh, this is very interesting questions. Actually, the variation can be between of a factor between 10 and 90%, depending on the viewing angle. It also depends on the overall dust content. I don't have a slide that can easily quantify this, but yeah, we can discuss more on Slack.
One more question. Is the difference between sources A and C due to beaming or evolutionary stage?
That's also a very good question. It is due to the evolutionary stage. For every line of sight, it is true that source C is dust obscured. At least in this simulation, at this snapshot. You're welcome.
Thanks. All right. For the sake of time, we can have more discussion in Slack. And let's move on
sure. I'll go to Slack.
Great talk. And then move on to the last talk for today is Sherry Johnson. Extreme primordial star formation enabled by high redshift quasars. Jared, go ahead.
Great. Is everyone able to see that?
Yep.
Great. Yeah, I appreciate the chance to speak with you all today. And the question I'm going to be addressing in this talk is really, is it possible, although perhaps not necessarily likely, but is it possible that with future observational facilities, we'll be able to detect primordial star-forming galaxies? And I'd like to kind of couch that topic in a bit of the historical context. So I've decided to make a timeline going back now 20 years of the sort of number of claims that we've seen for possible POP3 detection and searches for POP3 star-forming galaxies. This goes back to Malhotra and Rowe's paper in 2002, where they claimed potential POP3 powering of a Lyman alpha emitting galaxy at redshift 4.5, and it extends now into 2020, actually, with a couple of recent papers, one by Vanzella et al., claiming potential POP3 source in a strongly magnified field at redshift of 6.6. So there's a lot of activity that's been undertaken, but of course there's nothing definitive in terms of a firm POP3 detection. So those types of first stars remain elusive. This kind of thing could change, though. The state of the field could change. Of course, we have new facilities coming online, which have as their goals to peer deeper into the early universe and search for such objects. Principal among those is probably the James Webb Space Telescope, which is still scheduled for launch in 2021. It will replace the Hubble, and of course is optimized in the infrared to do these types of searches. It's not the only thing, however, that we've already heard today mention of the extremely large telescopes, the sort of 40-meter class telescopes that will come online a few years later. Will also push our boundaries back into the early universe. So right now, it's actually critical, I think, to make predictions for where primordial objects could be detected or how they could be detected, because these observatories are going to be coming online, and those predictions will be needed in order to strategize how to use those facilities. So when you ask the question of how can you find primordial galaxies, and sort of unpacking that, one of the questions that comes up immediately is, well, which population 3 stars are you really hoping to find, right? So the first stars we believe formed in high redshift many halos, maybe at around a characteristic redshift of 20 or so, and dark matter halos with masses of order 10 to the 6 solar masses maybe. And there's a nice, I've taken a nice figure from Hirano's paper showing sort of the mass scale of stars that you expect to form in those objects. And it's been known since the planning stages of James Webb, right, that those objects would certainly be too dim for James Webb to detect in the absence of some kind of extreme gravitational magnification, maybe. And it was thought that you may have to have a collection of population 3 stars in a cluster, maybe as massive, upwards of even 1 million solar masses or so, for a definitive detection. And so this points you immediately at sort of a couple of the characteristics that you'd expect for a POP3 cluster to have in order for it to be detectable, right? One of those things is a large stellar mass. You want it to be bright, of course. The other is actually a low formation redshift. If you can detect something, or excuse me, if a cluster forms at lower redshift, redshift 6, let's say, as opposed to redshift 20, of course you have a better chance of detecting it as well. So I'm going to go through both of those sort of criteria one by one. The first one is really what's required for POP3 stars to form at relatively low redshift. And there's actually a bit of observational evidence, at least on the front of the basic ingredient for primordial star formation, right? Which is that you have primordial gas available. So now we have observational evidence from Lyman limit and damped Lyman alpha systems that have been observed all the way down to redshift 3 or so that are consistent actually with those gas clouds being uncontaminated, being primordial in origin. So from the empirical side, at least, there is at least evidence for the basic ingredient for primordial star formation way down to low redshift. On the observational side, you also have evidence that population 3 star formation extended down to low redshift. This comes from a body of increasingly sophisticated cosmological simulations that have been done over the last 10 years or so, showing that star formation, the POP3 star formation, though it starts at redshift 20, does continue steadily down, maybe to redshift 6 or even lower redshifts. This is a plot from one of our papers, and you can see the population 3 star formation rate is shown by the dashed lines there. The key point here being that it does continue down until the end of the simulation at redshift 6. So you do expect from the theory side as well to have some primordial star formation taking place at low redshift. So then the next question, right, is if you do form population 3 stars at low redshift, how many can you gather together in a cluster, and can it be bright enough to be detected? The main way that we envision primordial gas collapsing to form large clusters is really by delaying its collapse until you have a large gene's mass, and potentially a large influx of gas ready to form stars. And this is usually envisioned as happening in an ionized region of the universe, because the gas is maintained at an elevated temperature and is only able to collapse once a lot of gas is assembled. In a typical reionized region of the universe where the gas is maybe 10,000 Kelvin or so, it's really only in halos with masses of about 1 billion solar masses or so that you may expect the gas to finally collapse. Now keep in mind, this is 1,000 times larger already than the many halos at redshift of 20, where you may expect the first stars. And so you have at least potentially a large reservoir of gas from which to form a relatively bright cluster of population 3 stars. Now, the key point here is that if you not only look at a sort of run-of-the-mill reionized region of the universe where the gas is 10,000 Kelvin, but instead look at a special region of the universe where it's heated to much higher temperatures, there's the potential for even more massive halos to host the first episodes of star formation. In particular, I'm thinking of the regions around high redshift quasars. So we know that high redshift quasars are there, and we know that they emit copious X-rays, which heat the gas to very high temperatures, maybe approaching even 1,000,000 Kelvin in the IGM. At these types of high temperatures, it's really a mass scale for the halos hosting those first stars that approaches something of order 10 to the 10 solar masses or so. So this is really the extreme case, the most massive halo you could envision hosting the initial phases of star formation. But keep in mind, right, the key point here is that the reservoir of gas in a halo that large is so large itself that even at a very small star formation efficiency, so even if only a small fraction of that gas forms stars, it may be a relatively bright POP3 cluster that can form, and maybe something of order of 1,000,000 solar masses that would be definitively detectable by James Webb. So one of the observational results that got me interested in looking at this scenario a bit more closely is from Goto et al. In 2017. I've taken a plot from that paper here. What they did was a search around a high redshift quasar at redshift 6.4 to look for Lima alpha emitters, and actually found only an upper limit. They found far fewer than they would have anticipated if those things followed the luminosity function at redshift of 6. This seemed to imply that the feedback from the quasar was actually suppressing star formation in relatively low mass halos. And in fact, it was consistent with suppression of star formation in halos of about 10 to the 10 solar masses, just the mass scale that I mentioned in the last slide that you'd expect potentially around a high redshift quasar for star formation to initially begin. And so this is, some observational evidence that we already have is consistent with the picture in which you may have the stage set for a burst of relatively bright primordial stars just in the surroundings of high redshift quasars. So motivated by some of that work and what I've shown already, Aikutal, a postdoc here at Los Alamos, and I decided to look at the evolution of that primordial gas as it collapses into a halo of that mass scale. And we took a simplified approach. I won't go into the details of the calculation shown here. I'll just draw your attention to the sketch at the top. The basic picture we have in mind, right, is that there's a supermassive black hole accreting gas and a high redshift quasar, and there's an accompanying stellar population in the host galaxy. All of these objects are producing X-rays, Lyman-Werner radiation, optical and infrared radiation that has an impact on the chemistry of the collapsing primordial halo. And then we ask the simple question, what happens to that gas as it collapses, given that it's subjected to such an intense radiation field? So what we found actually is that there are two basic possible outcomes that we'd anticipate. The first is that if the gas is able to cool, you may anticipate a population 3 stellar cluster forming, maybe one that's very bright because of the sheer volume of gas in the reservoir. The other one is that if the gas is maintained at an elevated temperature, you may have the scenario taking place, which we've already heard about today, the direct collapse black hole outcome. And there's sort of a characteristic distance from a high redshift quasar within which you might expect a direct collapse black hole to form because the gas is maintained at high temperature. And what we found here for sort of typical high redshift quasar black hole masses and stellar population mass, something of order 200 kiloparsec or so from a high redshift quasar that you could have direct collapse black holes forming. So keeping that length scale in mind, a couple of 100 kiloparsec, we can now ask another question, which is really a key one, and that is, what about metal enrichment? So metal enrichment we would expect to occur from high redshift quasars. Of course, they pump out the radiation that sets the stage potentially for a burst of POP3 star formation, but the metals could enrich the gas and actually prevent POP3 star formation as well, at least in principle. What's been seen in observations, however, though, is that metal enrichment and the outflows from high redshift quasars appear to extend only out to maybe kiloparsec or maybe a couple or a few tens of kiloparsecs from the host halo. And that is a shorter length scale than the sort of hundreds of kiloparsec we're looking at in terms of the distances of these interesting primordial objects. So I don't think that necessarily metal enrichment is going to be a game or a showstopper in preventing this scenario from taking place. You also incidentally see the similar results from what's found in observations in recent cosmological simulations. So another thing that we went on to do is actually look at, how bright would you expect these objects to be if you form a cluster of population 3 stars, again, assuming a pretty low efficiency for star formation, but a very high halo mass. You can see in the plot here, we have Lyman alpha flux as a function of redshift for host halo masses corresponding to 3 different virial temperatures between 10 to the 4 and 10 to the 6 Kelvin, 10 to the 6 being really that extreme upper limit you might expect for initial stages of star formation in the vicinity of a quasar. And the key point here is that we've also plotted the NIRCam flux limit expected for James Webb for an observation time of about 2 × 10⁵ seconds, so a couple days maybe. And the point here is that you really do need to have these stars forming in really massive halos in order for James Webb to detect them. So you really do have the best chance potentially of finding POP3 clusters in the vicinity of quasars where the most massive clusters could form. Another point related to that, though, is actually that direct collapse black holes, if they form instead of just a simple stellar cluster, because those are powered by accretion onto the black hole, they can be brighter, and they may also be more long-lived sources, so that surveys looking for these things may actually be expected to find more direct collapse black holes than POP3 stellar clusters, for those reasons at least. So I'll come to essentially my last slide here, which is to make a point, which is key, and that is that there's an elegantly simple observational strategy for testing this scenario and potentially finding primordial stellar populations in the high redshift universe. And it doesn't involve doing a deep, wide, very time-consuming survey. The nice thing about this scenario, right, is that you already know where to look for these objects. We already know where high redshift bright quasars are, and you can do individual pointings of those objects and look around their vicinities and see if you find any of these interesting primordial objects, be they POP3 clusters or direct collapse black holes. I illustrate that point here by showing the James Webb NIRCam field of view sort of superimposed on the Wu quasar from the discovery paper in 2015. You can see how large that field of view is. And I've also shown a circle here of that length scale within which you may expect POP3 clusters or direct collapse black holes to form. You can see that the James Webb field of view fits snugly over that. So with just a few pointings, you might have a chance at finding something really interesting in a limited amount of observing time. And with that, this is my concluding slide. I'll leave it up in the interest of time and take questions. Thanks.
Thanks so much. It's exciting. I will allow people to applause while we're waiting for questions. Any question for Jared? Sorry, any question for Jared? So Jared, can you show the prediction of how bright these POP3 clusters are again?
Yeah, let me share once more. Yeah, so maybe this is what you would like to see. Yeah.
I'm just wondering, so the JWST NIRCam limit, that limit, in which sense that's the limit? How long exposure?
Oh, I'm sorry, yeah, this is something I sort of glossed over in the bottom left. It's this is for a 200,000 second exposure, so it's a lengthy exposure.
Okay, thank you.
Yeah,
We have one more question. Would the duty cycle quasar affect the formation of these POP3 galaxies?
Yeah, absolutely. In principle, it does, right? Because if there's, I mean, the star formation has to be suppressed from the time those are mini halos all the way up until they're these relatively massive halos north of 1 billion solar masses. Star formation has to be suppressed that entire time. So the quasar probably has to light up early and suppress star formation, for hundreds of millions of years. Of course, if it flickers on and off, that could leave windows when primordial star formation could take place, and you miss out on this scenario. So that is a really good point. One of the things we looked at in the paper, though, is I'm flipping through here. You can sort of mock up the kind of radiation field as it would evolve in time, starting from the seed black hole at earlier times. And if it's steady accretion, it looks like you have a chance of actually accomplishing that suppression. But I completely appreciate the question that if there is a duty cycle, it complicates the picture for sure.
Thank you. We have one last question before I think we close off for today. So Rohan has the last word. How would you confirm sources around these quasars as POP3 clusters? Will their signatures differ from the canonical expectations in any way due to the quasar environment?
Yeah, Yeah, that's a wonderful question, right? It's a broader, and really key question that I haven't even attempted to address in this talk. How do you prove anything's a POP3 source, right? I think what you'd have to do here, of course, going back to what Eduardo said to open, there's the distinction between detection and identification, right? James NearCam can probably provide a detection, but the identification will be the job of probably the NearSpec instrument. You'll have to take a long spectral measurement to see if you find lines like the helium-2 1640 line, which is thought to be a signature, and push down upper limits for the lines from metals that may be there as well. But how far you can afford to do that and really prove something as POP3 is a fantastic question. And I don't have a great answer for that.
Thank you. As for the next JWST proposal cycle, I guess.
That's right. I think.
Yeah. So there's some more questions in Slack. You can continue discussions there. This is the last talk for today. Sarah, do you have anything for the audience?
I'd like to thank everyone for coming to this first day, and hopefully see you tomorrow at the same time.
All right. See you tomorrow.
Thank you. Bye-bye.
Bye-bye.
Thank you.
Bye.
See you tomorrow.
Thank you.
Bye.
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 Sarah, is there more recorded talks? Are there more recorded talks?
They're all these talks have been recorded live. And
No, I mean, are there more talks that will be pre-recorded?
There's
there
only
is
one
one.
tomorrow. Yeah, I figured out the solution to the problem. I have to play it from not the host. If I play it from the host, it goes as a feedback. But if I play it from my personal laptop, it'll work.
I see.